Okay, so now this way of doing things has another interesting feature, and I won't kind of prove it to you, but it's so plausible when I tell you that you'll believe it, and then you can look at our paper to see more detailed thing, which is, so these particles, these underlying particles are massive. The other guys are massless. Now it's a very natural question. If you take the high energy limit, what should happen? If you imagine all these particles have incredibly high energies, what should you expect that these massive amplitudes should turn into all the different helicity amplitudes, right? All contained in the massive particles.
It depends how mass is acquired.
Sorry?
If it's through Higgs mechanism.
No, that should be true in general, and it's that's actually, well, when we talk about the Higgs mechanism, we'll see that. So the question, there's a separate question of whether the high energy behavior is good or not. That's what the Higgs mechanism is about. But the fact that when you go to energies above the mass, you see in the Higgs mechanism you have the mass of the W, and there's a large range of energies parametrically above the mass of the W, but beneath 4 pi, the mass of the W over G, where the theory is still weakly coupled. And in that energy range, just kinematically, you have to see the massive amplitudes turn into the component massless helicity amplitudes. Okay, so that's just group theory. That's not physics. So the question is, so how does it happen? So how do you think it happens here? How do you think from this expression we can figure out what all the component helicity amplitudes are when we go to high energies? Erase the bars. Okay. Now this is an illegal expression, right? And that tells you what the different helicity components are, right? So this is a component. That's the amplitude for the piece of the spin 1 that has helicity -1. This is the component for the piece of the spin 1 particle that has helicity 0. Okay? And so merely by erasing the underlines or by unbolding the characters in tech, you go from the massive amplitudes to the massless ones. Okay? And this is why it was so important that when they were massive, there wasn't this GL1. So that's what allows us to sort of add these pieces together when it's massive, that then when we erase the underlines, just turn into the different helicity components as we go to high energies. Okay, so that's our first little hint of the simplicity of this formalism.
If you have a hierarchy of scales of scalars, is there something special in these amplitudes?
What do you mean?
So, I mean, I just want to see, is there some, can we see something like the hierarchy problem in amplitudes?
No, well, in fact, no. I think this is something that we knew, but there is, when you think on shell, you never see any analog, you don't see any avatar directly of the hierarchy problem, ever. Okay, that's because there isn't, from that point of view, from writing down an S matrix with the right rules and so on, there is no hierarchy problem. In that language, it's translated as it is in field theory that nothing tells you how to calculate the mass of the Higgs. Okay? And if you're talking about the hierarchy problem, I think the cleanest way of talking about it is to refuse to talk about it in the context of the standard model. In any theory where the Higgs is a parameter you have to take from experiment, you don't have to talk about it. You can just say it's philosophy, you can forget talking about it. However, it has teeth, it has real teeth, and this is why model builders get annoyed when people talk about, oh, it's all philosophy, blah, blah, because model builders do work to find theories where you can calculate the Higgs mass, right? Forget about solve the hierarchy problem. Just calculate the sign. Is it positive or negative? You know what? So you want some underlying structure where the Higgs mass squared is calculable. And the real teeth of the hierarchy problem is that for the 40 years people have thought about how to find such a structure, every example that we found has this feature, that the physics that makes the Higgs calculable, be it compositeness, be it supersymmetry, be it extra dimension, be it any of these things, that all has the feature unless you make now in this new theory clear tuning where it's calculable, so you can do it and you can see the tuning that you have to do. The Higgs never comes around alone. It comes with a lot of other stuff along for the ride. So from that point of view, what you're looking for, translated in the S matrix point of view, is some theory where the kind of high energy limit doesn't have any parameters that correspond to the mass of the Higgs, and then the masses are generated in some self-consistent way from consistency of the S matrix, and maybe it's just a feature of all the theories that we've tried, but it's 4 decades of trying, so we haven't. It's not some like stupid thing. But the other way, just in the standard model, of course, you don't see a hierarchy problem from this point of view. From the on-shell point of view, you don't even see a quadratic divergence. You don't have to see anything that looks like ultraviolet sensitivity, nothing. All you have to put in are the branch cuts you need to give you the logs you need, and you never see even the notion of ultraviolet sensitivity. So it's really a statement about theories people have found which managed to make the Higgs mass calculable. And as I said, when I was a grad student, I was charged on some paper I was working with my advisor and others to be the student putting in all the numbers and checking everything and so on. And so I had to put in numbers in order to make everything work in our theory of supersymmetry breaking. And I remember very well sitting, late at night in my office and trying this parameter, that parameter, and it just didn't work. I couldn't make anything that gave a reasonable spectrum. So I went to my advisor and I said, there's something wrong with my code. I can't. And we gradually realized it's because there's fine tuning in supersymmetry, right? And the fine tuning I was like doing by hand on the computer myself to find parameters that actually worked, okay? And I could barely find parameters that managed to be compatible even with the limits on the Higgs mass that existed back then. So it's not a joke. When you have a theory where you can calculate it, you see, it hits you in the face what tuning means. On shell, you will never see it. I think it would be, no one has done it explicitly. I think it would be a nice pedagogical kind of a polemic exercise to show when you calculate things on shell, you don't even see a hint of ultraviolet sensitivity. Never mind quadratic divergence, which is meaningless anyway. But even as you say, you put in heavy particles, you would not see any of it. Absolutely.
It's kind of
What
basic.
will you do with non-stable particles?
Sorry?
What you will do with non-stable particles?
They should show up in the usual way as poles on the second sheet and so on and so forth. So I don't think we have anything really new to say about any of that. Okay, so let's see. So now we've been talking about massive amplitudes for a while. You were the person who asked, I guess, right? So you have not learned anything new yet, or? Okay. Okay. Let's see. Should we? So maybe you can say, what do you know already? Is there something specific that would you?
I think one thing I didn't understand in your paper was how exactly you took the high energy limit.
Oh, you mean by erasing the bars?
You don't do it
Like this in the paper.
You have that expansion into, what do we call it, eta and epsilon. Yeah, eta plus and eta minus.
That's too bad that we didn't do it that way. No, we did it this way in the paper as well. In fact, the thing is that that there's only some very exceptional situations involving funny kinematics like the 3-particle amplitude where it matters. So, but beyond 3 particles, when you don't have funny kinematics, you just drop the bars and it just works. So, but it does matter for 3 particles. You're right. So yeah, we could talk about that. We could talk about but what is it? You want to see how you pick out what the correct 3-particle amplitudes are?
No, so you have these arguments when you take the high energy limit where things become singular, and then you say that that's why you can't have massless high
Right.
spins, or massive high spins can't be elementary.
Right.
You have a very specific way in which you take that.
Yes, yes. Well, I mean, it's not a way. It's just taking the high energy limit. But it's no. Well, the argument why massive higher spins can't be elementary has nothing to do with the three particle amplitudes. That just has to do with that's yeah. I mean that. But for massive particles, you just calculate the amplitude, and then you just see what it looks like at high energies. There's no difficulty per se taking the high energy limit. You just go to high energies and see that it has pieces where the 1 over m's don't where the 1 over m's don't drop out. I mean that I should say that. We did it explicitly so one could see how it works, but it's guaranteed ahead of time that something like that had to happen, precisely because the high energy limit for the massless particles does not exist. So maybe that's what I should have said here, is that when there is some, when there is something you can match to at the high energies, then this has to be the answer, right? You just drop the bars, and if there isn't, then if you're worried about powers of 1 over m and so on, that's what happens in these examples. Then you have to be more careful. But yeah,
What was the difference between
yeah.
that case and the graviton amplitudes?
Sorry.
What was the problem with taking the high energy limit with the graviton? Sorry, what was the problem with taking the high energy limit on the high spin amplitudes compared to the graviton amplitudes?
Oh, okay. So this has nothing per se to do with massive particles. There's a whole story. So well, let me say something about this. Actually, these things are all related. So let me say something about this. So well, first let's just say something about three particle amplitudes for massless particles. So if you have just three scalars, so you guys probably Newton, I'm sure, told you about all these things. So if you have just no spin, it's just a constant, it's some g or something. Let's say it's a, let's say we have two fermions and a scalar particle, then this is still something like this. Okay? So everything is fine. Everything is fine, by which I mean it's just a simple, it's polynomial, right? It just looks like, but famously, when you start getting to higher spins, so scalars and spin a half, everything is simple. But when you start getting to higher spins, like Yang-Mills, then we start getting these things like G 1, 2 cubed over 1, 3, 2, 3. Okay? And, we write these things down. They're fixed by symmetries. Everything is fine. But this should bug you. Okay? There's something weird about this formula, which is this three particle amplitude itself already has poles. It has poles in, it has these angle brackets downstairs, right? So that's peculiar. We're normally used to thinking that poles means something, the amplitude factorizes, there's something going on, that poles associated with dynamics. And here this is already in the three particle amplitude, we have poles. Okay, so what does it factorize to? What does this pole mean? So this is strange. The fact that these three particle amplitudes have poles is weird. The only reason it doesn't indicate some kind of non-locality is simply because it vanishes in Minkowski space. Okay? So in the limit where we go to Minkowski space, remember, in this configuration, the lambda tildes are parallel to each other. The lambda tildes are parallel. So if I can't, if I'm in Lorentzian signature, that means the lambdas are also parallel, and because of the cubed upstairs, this whole thing vanishes, right? So that's a very important reason why we write down that combination, for example, and not the inverse of it with angle replaced with square brackets.
Again,
So,
if you
yeah.
have a non-stable particle, then this doesn't, then this survives.
Well, no, because if these particles are massless, they're all stable. That this does not represent a decay, right? Yeah. Okay. Now, so just to show you that this is not a total triviality, let me write down another 3-particle amplitude. How many of you have ever encountered this sucker? Let's see. Yes. Okay. How many of you have seen that 3-particle amplitude? Okay. Well, what do you think about it?
Doesn't come from like a local.
Yeah, there's no Lagrangian that gives you this guy, but who cares?
Yeah. If that was the 4-particle case.
Sorry? There is a 4-particle test, indeed. And so the real problem is that this guy, you try to build a consistently factoring 4-particle amplitude with it, and you can't. Okay? So it's ruled out for that reason, which is a good thing because this is a phase in the Lorentzian limit, right? It doesn't vanish. So this would be something very weird and bad. So these things come from Lagrangians, even though they have poles. Somehow it's related to the fact that they're okay in Lorentzian signature. I'm not thrilled with this argument because everything else in this subject, you're very signature agnostic. Okay, so it's a little bit funny that the behavior of this in Lorentzian signature is somehow so important. But in any case, there is something odd that once we start having particles with, once we start having particles with spin, that the 3-particle amplitudes have this whiff of non-locality about them, despite the fact that they're not really non-local in any sense. They vanish in Minkowski space. And when we use them to try to build 4-particle amplitudes, they can factor consistently. Okay? But the fact that the 3-particle amplitudes have poles in them already makes it non-trivial that they can factorize consistently. So let's contrast again with, did you talk about all this stuff, Yutin? You probably talked a lot about 4-particle factorization for massless particles.
Yeah.
Okay, great. So I won't. Okay, great. So then, okay, great. So, all right. But here already we see that as the powers get larger and larger downstairs, when you glue together 2 3-particle amplitudes to get a 4-particle amplitude, the problem is that it's not obvious that they don't have poles in the other channels. And then as you go to high enough spins, eventually you're screwed. Okay? Now, that's the problem. That's the problem when the particles are massless. What about when they're massive? When they're massive, now we can go through the whole massive formalism and write down the different 3-particle amplitudes and so on. But just to give you a sense for what's going on, when they're massive, roughly speaking, the poles are gone, but they're replaced with the masses. Okay, so instead of having these guys downstairs, you get factors of 1 over mass downstairs. And so you trade the problem for something else now. Now there's no problem gluing. You can glue anything together to build something that factorizes consistently, no problem. But now it's not remotely guaranteed that the high energy limit doesn't have factors of 1 over m in it, because there's 1 over m's in the scattering amplitudes at 3 points. Okay? And so the same thing before in the massless limit that prevented you from taking that made it just impossible to factorize properly. And it was impossible because the degree of the poles was too high. Okay, so that you couldn't match it with something consistently in the other channels. When the particles are massive, makes it impossible for them to have the right high energy limit because there are too many factors of 1 over mass downstairs in the 3-particle amplitudes. Okay, so that's the reason why it was kind of guaranteed that it couldn't work, right? When you had massive particles with spin, coupled scattering, and notice that it was the same scattering amplitudes that we use. The scattering amplitudes that tells you the massless higher spin particles can't exist are the scattering against gravitons. Okay, the amplitudes that tell you that the high energy limit cannot be well behaved is with gravitons again. It's exactly the same thing. I should say another general fact is that the reason why the scattering off gravitons is such a ubiquitous feature of the tests of the consistency of scattering amplitudes is very closely related to what normally in local quantum field theory we talk about is the ability to have an energy momentum tensor. Okay, so the ability to having a local stress tensor is a big constraint on local quantum field theories. In the amplitude language, it's precisely translated to the ability to couple to gravity consistently. Okay, so you should expect that what in standard field theory is done by asking about matrix elements of the stress tensor, a la the Weinberg-Witten theorem, is reproduced by something about graviton scattering from the on-shell perspective. Okay, so it's not a surprise that we keep scattering things off gravitons to discover these things about the inconsistency of massless higher spin particles, or the inability for the massive higher spin particles to they have to show substructure in the way that we described. So what we did is just do the gluing of things together, and just there's nothing goes wrong. You just get the answer. You take the high energy limit and see that what survives has these factors of 1 over m in it, but it had to for the reason that I mentioned. Yes.
Yeah, maybe continuing a bit mass project. Maybe about massive amplitudes. So I'd like to find some fundamental interesting structure for massive amplitudes, because actually, in principle, you would think that mass should be probably like dynamically generated ideally, like because you can't it's hard to imagine a fundamental mass of the parameter, right?
Well, let me. It's hard to say anything on in very general grounds, but let me give a limited answer. So first on general. I mean, you asked a philosophical question. I can give a philosophical answer at the most general level. That I think I was saying this outside. I think that it should be the case that the closer and closer you get to describing the real world, the better and better things should become, not worse and worse. And this could be wrong, but it's an attitude that has not. It's certainly not led. It's not let any of us down yet anyway. So you might think that, everything that nice that happens is for special, simple theories, n equals 4, blah, 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 and the real world is messy and complicated. And that would be true if the reason for all the things that were going on was just a bunch of tricks and something special that happens here or there, and fine. But if the reason the things that we're seeing are that there's some deep structure that lives at infinity or somewhere else that is responsible for space-time and all the stuff that we're talking about, then if it's a property of the real world, we have to see it everywhere. And probably the closer we get to the real world, the closer we get to what's responsible for it. From that point of view, massive amplitude should be better. And why don't they look better? Well, before we knew how to look, you see that whether things look good or bad is a very non-invariant. It depends on human beings. It depends on where they are in their understanding of some subject. You can't decide whether they look or bad until you figured out whether you're listening correctly to what the thing is trying to tell you to do. And all I can say is this. If we talk about the more technically, all I can say is that, for instance, this description of the Higgs mechanism that we gave in the paper with Yutin, in a very concrete way, it shows you take a bunch of disparate helicity amplitudes, and they're combined into, a smaller number of terms in the massive amplitude. Now, it's literally like grand unification, right? Except it's grand unification for the little group. So you have all these different helicity components, and they get unified into SU2s for each individual external leg. That's really interesting. It's exactly the opposite of the psychology that the Higgs mechanism is breaking something. Something used to be beautiful and it's being broken, right? Here it's the other way around. There are a bunch of things that were not unified, and they get unified by getting Higgsed. I think that we will see this most clearly on the Coulomb branch for n equals 4 super Yang-Mills, if you want to see some evidence for magic. And I think it's inconceivable that there isn't some remarkable theory on the Coulomb branch. Amongst other things, this theory should combine all the different helicity sectors together into one object. And that's a good thing. You know, it's a bad thing that the different helicities are split into different pieces. Physically, when you go on the Coulomb branch, many things happen. The amplitudes become perfectly well defined. They don't have infrared divergences. Everything becomes sort of better, and they should get unified somehow. Do we see how to do it now? No. Did we know 10 years ago, 20 years ago, that literally 30 years ago, did we know that MHV amplitudes are like one-liners? Barely. Okay, so. I think it's a matter of studying them, finding the ways that they want to be understood, and then deciding. But you asked if I thought there was a structure, and I'm absolutely sure that there is a structure. And I think, you know, even at the most basic levels, we're seeing it already with how Higgsing is unification from the perspective of the little group, not breaking. Higgsing is actually unifying, not breaking.
Is there any geometry that arises in massive amplitude?
We don't know yet. We don't know yet. There is some. I think all I can say is that there is this vague idea that all of this positive Grassmannian structure. There's the kind of GL version, the SU version in some language. That's relevant for n equals 4. There's the SO version that's relevant for these ABJM theories. But there's been this SP version of the positive Grassmannian story sitting around for a long time, not doing anything. And there's many indications that it's related to 6-dimensional scattering amplitudes. It's related to, somehow perhaps related to the physics of the Coulomb branch for n equals 4. I think there's still nothing very concrete about that yet. But it's something that's sitting there that needs a purpose in life, and it seems very natural that its purpose in life should have something to do with massive amplitudes.
But there are recurrence relations, are there?
No, not yet. Not in a really workable way. No. We should distinguish. There are many kinds of recurrence relations, some of which have sort of no magic in them at all. There are just other ways of doing bookkeeping, and some of which, like BCFW, have magic. BCFW has some real magic. There are other things that have much less magic in them that you can do, but they're very generic, and you don't learn that much from doing them, from my point of view. BCFW is a thing to try to figure out how to do for the massive amplitudes. The problem with it is that without supersymmetry, when you do you have to be careful how you do these BCFW shifts. If you do it on the wrong helicity components, it doesn't work. When you have massive amplitudes, precisely because they combine all the helicities together, you worry that when you shift them, that you're shifting everything, and in particular, you could be shifting the wrong things, okay, which are in there. So that's the kind of qualitative challenge. I honestly have not thought about it enough to know how hard this problem actually is. But all I can say is that if you have maximal supersymmetry, then if you shift in a way that's compatible with supersymmetry, everything is just flat out work. Because that's what happens when it's massive, or that's what happens when it's massless. And the supersymmetry is smart enough to take care of all of the details of how the shifts actually work. So that's why the Coulomb branch is a great place to start. Because if we can understand how to set up the 3-particle amplitudes and on-shell gluing and all of those things just at the most basic level, then I think the whole story should just, systematically proceed the way it did in the massless case.
But the derivation of recurrence relations in massless case are based on behavior of at infinity.
Which should not be messed up by the masses. That's the point. That's right. That's why it should be okay. And in particular, in n equals 4 super Yang-Mills, the symmetry way of saying why there's nothing at infinity is dual conformal invariance. That's equally good on the Coulomb branch. So everything is fine. There's no reason. I really feel everything at the moment is just technical. The technical stuff is pretty annoying though. So there's a fair amount of just stupid group theoretic struggle with figuring out how to label the states on the Coulomb branch nicely. There's a tension between keeping the R symmetry manifest and keeping well, anyway, there's some kinematical difficulties.
But this kinematical, you can forget about n equal to 4 and consider simply massless bosons.
That is perfectly fine. That is perfectly fine. And then there the difficulty gets translated to the other thing I was telling you. When you have massive particles, you don't know how to shift them. Because if you do a generic shift, you worry that in the massless limit, you're shifting both the good combination and the bad combination. So for example, for spin 1, you can shift, I forget which one it is, plus minus, but not minus plus. So you can do plus plus and minus minus, and one of plus minus, but not the other one, minus plus. But when they're all massive, you shift them, how do you make sure that you're not shifting the bad one too? The thing is that when you do things on shell, everything takes care of itself, because you're not shifting anything. You're not actually shifting. You're taking some amplitude, and then you're doing something sort of more canonical. You're gluing these three particle amplitudes, and when you do this supersymmetrically, it just does what it has to do, right? So we should just figure out the analog of that is on the Coulomb branch, and they won't have these colors on them. So it'll be something more, because the second you make things massive, then you lose this distinction between the helicities. That's also, by the way, a good thing in n equals 4. In n equals 4, it's something you get used to very quickly. It doesn't matter how you color things. It doesn't matter what kind of bridge you put on, whether you make it white-black or black-white. But those are in components, they're pretty non-trivial facts. It's a fact that it's not been used that much. The fact that you can color things any way you want as you go along to do the shifts is you can't. But it's a feature of the massless theory that has not been exploited. This will force it on you, because somehow the massive 3 particles would really be some symmetrized version of both of them. So yeah, I mean, there's a lot about the symplectic Grassmannian that smells right. The analog of their Plabic graphs also has some symmetrized version of white and black vertices and so on. It kind of feels like it looks like Higgsing. But beyond that, well, there's some people here who have been thinking about this more recently. Your guys' paper has something, I read something in the abstract about the symplectic Grassmannian.
Yeah, not much.
Okay. It was in the abstract, though. Right. Yes?
Yes, a couple of speculative questions. Do you think there might be a positive geometry related to like a normalization procedure? Oh,
yeah. Sorry, I hope so, but I don't know. I mean, I think that's the, that's the, I mean, if you were to ask me, the question, what in this whole program, what am I most worried about? What am I most worried about that could be an indication that it's completely not going to, there's a dead end at the end of this long road. That's what I'm the most worried about, okay? Is exactly this issue of how the RG is going to come out. At the same time, I'm also the most excited about it in the opposite direction. But indeed, the thing is that when you think about scattering amplitudes, and you want to go to war with local quantum fields, right? If you want to go to a war against local quantum fields, the place to attack local quantum fields is scattering amplitudes. That's the place to start, because that's the place where the standard way of doing physics is at its absolute weakest. Okay? And the reason is that it's already already used. We've said local quantum fields are great in Euclidean space. Haha, you go to Lorentzian space, so it sucks, right? And also local quantum fields are great at local questions. So haha, you ask a very non-local question. You scatter particles in from far away, blah, they hit each other, they go back out. So that there you're attacking local quantum field theory at its absolute weakest, which is good. You know, you want that's where you want to start. But if you're making progress, you're also making progress on something where the wind is at your back at 200 miles an hour. Okay, where is local quantum field theory the strongest is with the renormalization group. Okay, so and that a whole picture of effective field theory, decoupling of high energies from low energies, all of this fantastic facts that have also seeped into our very language in high energy physics. These are deeply Euclidean words. Okay, there is no decoupling between short distance and long distance in Lorentzian signature. Okay? There is no notion of short distance. You know, you can have points that are at 0 distance right on the light cone separated from here to the other side of the galaxy. Okay, so the whole idea, the whole notion of decoupling is a Euclidean notion, and the renormalization group is a completely Euclidean notion. I mean, I remember there's a natural question. If you're a grad student, you learn about asymptotic freedom. You're like, oh, this is so awesome. So when you scatter particles at really, you know, you scatter E plus E minus at 100 TeV, we can predict exactly what comes out. The experimentalists must be so happy. You go talk to the experimentalists, they're like, no, we're not happy at all. I mean, no one tells us what happens when I scatter particles at 1,000,000 TeV. It doesn't matter how high energy you scatter them. We get a big mess of spray of particles out, and none of the theorists can tell us exactly what comes out. Like, say, what the hell is going on? I thought there was asymptotic freedom. And yeah, it's irrelevant in the Lorentzian regime. Okay? So what you do is make average questions. So you can predict. You can say things about jets, you can say things, you look at the average amount of energy coming in this direction and that direction and so on. And what are those average questions? Those average questions are taking a Lorentzian question, and by some suitable averaging, you convert it to one that's Euclidean so that you can calculate it using asymptotic freedom and the renormalization group. Okay? There is not one feature of the real world, Lorentzian feature of the real world, direct Lorentzian feature of the real world that we can use the RG to control. The RG is a totally Euclidean idea, and we can then ask questions. Of course, we can ask questions with space-like momentum transfer. Great, those are Euclidean questions. Or even if we're scattering things at high energy in the S channel, we can do suitable averages, sum rules, things like that convert them essentially to Euclidean questions, and so then the RG is fantastic. So, okay, but now there's really a tension, because all the structures we see in amplitudes are very not Euclidean. That's the point. They're Lorentzian, they're dynamical. Heck, in the kind of geometries we're seeing, they're closer to 2-2 signature than they are to 3-1 signature. Okay, so it's going even further away from Euclidean space, and yet the RG is deeply Euclidean. So if there is some large animal that unifies all these different approaches to the subject, it needs to come up with a really good answer to the question of how to think about the RG. If it's not going to do it starting from, you know, these off-shell ideas, Euclidean space, local quantum fields, Wilsonian averaging, integrating out momentum shells, all these are phenomenal ideas, deeply Euclidean. I have no idea how we see them in scattering amplitudes. At the most basic level, when you compute the UV log divergences to one-loop amplitudes, something that's completely obvious from the standard point of view is that all of the ultraviolet logs go into the change of the coupling constants, right? That means from the perspective of the amplitudes that the UV divergent part is proportional to the tree amplitude. Now that's an amazing on-shell fact, that the UV divergent part of one-loop amplitudes are proportional to the tree amplitude. And you can ask any of the experts here who have looked at this if there's any picture for what the one-loop amplitudes are that makes that fact obvious. It's not obvious in any cut constructive picture of computing the amplitudes. That's the most basic level, and that's before getting to the real magic, which is that at 2 loops the leading log is proportional to the same thing that you saw at 1 loop, so that the logs exponentiate. Okay, so I think so So that's the reason to think that there's something missing, and there's some reason for pessimism. The reason for optimism is this equation. My favorite equation, which is, all of physics is one way or another the existence of the discovery of various structures that make this equation, that manifest this equation in some way. Okay, so that equation, which for a scattering amplitude person tells you that the poles of the amplitude, that the singularities in the amplitude are factorization poles and forward limits. Okay, this equation is also the Hamilton-Jacobi equation for the. It's also the Hamilton-Jacobi equation. It's also the equation for the boundary structure of the worldsheet moduli space, as you know very well. It's also the BV equation, and it's the renormalization group equation. Okay, so the Wilsonian renormalization group equation. Yes, it's also the Wilsonian normalization group equation. It tells you, as you change the cutoff of the theory, how does the effective action has to change to keep the physics fixed. And there's two things that can happen. You can, you can have one mode that's between the old cutoff and the new cutoff as you change it differentially, and another one where you close the loop. This is the Polchinski version of the Wilsonian renormalization group equation. So, so now it's just a formal similarity, but even the formal structure of this equation has been so humongously important in so many aspects of the story of scattering amplitudes. The fact that it shows up in the RG is very encouraging, right? So maybe there is somehow a larger structure that connects them. And I would say there is one other thing that I've always found encouraging, but I've had no time to actually do any real work on. But going all the way back to our early papers on shell diagrams, in theories with less supersymmetry, there's a Grassmannian picture for the corresponding on-shell diagrams, and exactly the theories which have ultraviolet divergences with less supersymmetry. They're associated with these other Jacobian factors in the Grassmannian form. And what's remarkable is that those Jacobian factors have singularities somewhere else in the Grassmannian. I think Alex really emphasized this to us early on, that these Jacobian factors, where they blow up, is precisely tailored to be not on the positive Grassmannian. So they have these sort of factors that exactly because of where all the signs are and so on, and the definition of the boundary measurements, etc., are such that they can never blow up in the positive Grassmannian, so they blow up somewhere else. So something just in the Grassmannian itself. There's a piece which is the positive Grassmannian that knows about factorization, it knows about all the long distance kind of singularities. And there's other part of the Grassmannian which is more mysterious, where these Jacobian factors blow up, which has everything to do with the ultraviolet. So we have just not spent any time there. I have not gone there to see what it looks like, really, in that part of the Grassmannian. But it would be worth to go poke your nose around and see what it looks like there, because the fact that they are literally split, geometrically split, is, I think, kind of is an interesting counterpart to UVIR, decoupling back in the field theory. So if something good is going to happen, I think it would have to start happening by looking at concrete things like that.
A more speculative question. So if I understand correctly, you hope that something like the amplitude hedron is this structure that we need to give speak of scattering with
right.
At infinity. No?
Yes.
But the fact that the amplitude hedron or the associated hedron, they looks a bit like the interior, sort of interior of external data. So for example, the associated hedron is literally the generalization of these momentum crystals, of the triangles, which are the interior of the momentum crystals. How do you feel about that? I mean, do you have an interpretation for this?
I think I don't have any. I mean, I have so little faith in any one of these interpretations that I don't know. I mean, for example, already this picture of the amplitudes as a form already changes this feeling significantly. Now you don't have any picture that you have some sort of fixed data sitting there and there's an inside and an outside and so on. Now there's just something else. There's a form that's defined everywhere, but the form has to do something. So now it's not a feature of the data, but it's a feature of the form that if you slice through the space of data with a certain kind of plane, then in a certain region it should have some nice property. But it's not like the data is fixed in any way. But more generally, it can't even be that any of this is the silver bullet, that all the amplitudes are a form or a silver bullet. After all, MHV amplitudes, they don't have any K, they don't have any Grassmann variables, nothing. And in general, they're complicated polylogarithmic functions and so on, right? So if there's some geometry, one of the things that it should do, and this is I think a much bigger challenge, is if there is some geometric structure at infinity, how does it manage to come? You see, for the integrand, it's at least everything is commensurate with what it needs to be. So if you're looking at 5 loops, okay, you have an integrand that depends on 5 loop integration variables. Everything is fine. However, if you only have the data at infinity, and all the loops have been integrated, everything's been integrated, if there's some geometric structure that lives there, how does sort of one structure have in it the ability to spit out, a dilog, a 4-log, a 6-log, a 10-log, an 80-log, right? So there has to be maybe there's a natural way of doing it, in which case that would be great. But I find that to be a more pressing question than worrying about the sort of precise. When there are integrands, tying them to a geometries with forms is a very natural thing to do. But that by itself can at most be some intermediate step to something more complete for the whole amplitude. So yeah, so I'm not ideologically married to any of these things, but I do think we're getting closer. I do think that seeing something in kinematic space is better than before seeing something in kinematic space, for sure. Okay, so I think we may not be close to the final ingredients, but we're going in the right direction for sure.
Okay, so I was quite surprised that Freeman Eisen had once said in an interview that he's not really he does not really believe in the existence of massless spectral particles.
Oh gosh, yes.
Yeah, so how confident are you on the existence of gravitons?
About as confident as I am in the existence of you. Okay.
Isn't the fact that we detected gravitational waves basically immediately means that?
No. No, yes, in any reasonable sense, but no in Freeman's sense. Freeman is a wonderful, iconoclast, incredible person. He never says anything stupid or wrong. They can be frequently annoying, precisely because they're not stupid or wrong. So his point is that it's very difficult to detect an individual graviton. I guess a graviton. There isn't a more diminutive word for it. A graviton, an individual graviton. And indeed, he spent a long time trying to conceive of crazy experiments that would allow you to be sensitive to measure individual gravitons, and he couldn't find one. So he likes to make the point that if you believe that it's important for a theory to be able to verify all of its individual components, that he can't imagine a single experiment that would detect single gravitons. So the fact that we see gravitational radiation of LIGO, you interpret as being zillions of gravitons, but we don't see the quanta separately. Okay. Related to that, just to depress you a little bit, you might think, and even sometimes when people talk about LIGO, they say things like, everything emits gravitational radiation, as we're moving around here, everything is just emitting gravitational radiation. And if it was true that we're emitting gravitational radiation, it would confer on us a certain amount of immortality. because something about our little lives would be transmitted by gravity waves going out into the universe, which are very unlikely to get absorbed by anything else. So some trace of us would be left out there, okay? However, I encourage you to do the very simple calculation. You can do whatever the hell you want. You can jump around, you can do any damn thing you want. You will not emit one graviton over the age of the entire universe, okay? So quantum mechanics actually, classically it's fine. You emit gravitational radiation, but because of quantum mechanics, you don't emit a single graviton. So this path of immortality is, alas, not available to us, okay? And we emit lots of photons, but they get absorbed pretty damn quickly before they go anywhere. So, any trace of their relationship to us is similarly lost. So, so the quantization of gravitons actually has consequences for massive objects. You don't emit gravitational radiation, much as you might like to. Huh? Yeah, you emit neutrinos, but okay. We don't have to talk about neutrinos. Yes. Yes.
Just to go back to the massive spinners for a minute.
Yeah.
In the paper you make some, you have a discussion about the high energy limit of a massive spin 2.
Yes.
And you point out a tension with the equivalence principle.
Right.
How is this compatible with what the massive gravity people like Claudia de Rham and others do? When they take a high energy limit and seem to get a sensible result.
Oh no, no. It's what we are doing is asking the high energy limit to match the correct high energy limit for massless particles of the right for massless particles of spin. We don't care about the odd integer spins, the odd half integer ones, but including massless spins 0, 1, and 2. Okay, and so the right thing that we're trying to match are the minimally coupled, in this case, theories where the only coupling is gravitational in the high energy limit, right? So that's exactly what works with the Higgs mechanism. So you take the conventional 3-particle amplitudes you have, and then you go to high energies and see if you match what you match at high energies the 4-particle amplitude you would have gotten from those guys. That does not happen for massive gravity. Another way of saying that is you can't Higgs gravity with ordinary stuff, which is why no one has seen it with, in any model with ordinary stuff. Now, what these models of massive gravity do is their high energy limit for the scalar components blows up at high energies much more rapidly than you would get from ordinary minimally coupled scalars. In particular, the 2-to-2 scattering amplitude grows like energy to the 6th. Okay, just for the scalar longitudinal components. These pieces go like s cubed. So, so in what we're doing with UTIN, we're explicitly not allowing that. We're asking it to just match what you get with ordinary minimally coupled scalars at high energy. So what we really do is prove on shell this statement that you can't obviously Higgs gravity with ordinary fields. Okay? But if you allow much higher energy growth for the 4-particle amplitude, you could, and that's how you could rediscover the like standard massive gravity. We didn't do that because that's much more close to what people have done. I mean, that's how Matt Schwartz and I 12 years ago started thinking about massive gravity again in this standard language of thinking about the just like people talk about WW scattering, looking at the effective theory for the scalar longitudinal modes. And the fact that it grows like energy to the 6th, now that has other problems. That's related to, that's why these theories also have problems with superluminality. They have problems with, anyway, they have other issues. But literally the question that we're asking is the analog of the question for massive spin 1, which is whether the high energy limit can match what you get from the 3-particle amplitudes of scalars, spin 1, and gravitons. And that they cannot do. So what happens in these theories is you have other 4-point couplings sitting there, contact terms sitting there for the scalar longitudinal modes. And that's responsible for this energy to the 6th growth. But just with putting in the physics of the minimally coupled particles at high energies, you can't match it.
I I thought the tension was in the three-particle couplings, that you got the wrong, like you should get a universal coupling to
Right. No, that's right. No. So but both things are they're so they don't have the I mean there's depending on what you want to do, you can move the tension around, but and in fact it would be a nice thing to do. I don't even know if someone has done it, but it would be a nice thing to do to actually to construct what. So here's a claim, and it would be nice to verify this claim on shell. The claim is that if you do a totally stupid massive gravity theory, then in other words, in the Lagrangian, if you just write down m squared h mu nu squared minus h squared, okay. So this is the Fierce-Pauli term. If you just do this and you work out what the scattering amplitudes are for the longitudinal components, the scalar longitudinal components of the gravitons, then so when you do the analog of this for gauge theory, for non-abelian gauge theory, so let's say I do m squared trace a squared. Then when I look at what I sort of expect for just with Feynman diagrams for the 4-particle amplitude, then my naive expectation is that these polarization vectors go like k mu over m. So these are going like energy over m. And so I would expect naively that the amplitude goes like g squared times e over m for each one of these things times e over m to the 4th. Okay? So you would think that that's the most naive expectation, that the amplitude that has this badly growing piece that grows from the longitudinal modes like energy over m. So it would grow like g squared energy over m to the 4th. Now, in fact, when you sum over all the diagrams, as you would expect, there's a Jacobi identity cancellation, and it's actually better than this. So this is wrong, but it actually goes like g squared e over m squared, which is still bad. Okay, it still grows quadratically with the energy, and that's why we had to have the Higgs to unitarize WW scattering and all the rest of it. Okay, but that's the usual story for Yang-Mills. For massive gravity, if you just put in the Fierce-Pauli term, if we do the analog of that, what would we expect? So now, first there's 1 over m Planck squared energy squared to begin with, doing nothing else. That's the usual expected dimensional analysis from gravity. On top of that, each one of these guys goes like e over m graviton for the polarization, for the scalar longitudinal mode squared. So you would expect that you get e over m squared to the 4th, so you get e over m to the 8th. So the whole thing goes like this funny e to the 10th over m Planck squared, the mass of the graviton to the 8th. Okay? And so, for example, you would expect that there's some breakdown of the theory at a cutoff comparable to this funny formula of m Planck to the 1/5, the mass of the graviton to the 4/5. Okay? Now, this is the analog of the stupid expectation about Yang-Mills, where something good happened when you summed over everything and the e over m to the 4th turned into e over m squared. When you do this for gravity, with massive gravity, with Fierce-Pauli, nothing good happens. This doesn't happen. It's exactly as bad as this dumb expectation. Okay? Now, what George I. Schwartz and I did a long time ago is from this analysis, from the sort of standard way of doing this analysis for WW scattering applied to this case, we saw that there's actually a way of fixing the theory, that you don't have to add just that Fierce-Pauli term. You could add higher dimension, you could add higher and higher order terms. And by doing that, it was possible to improve this. Okay? Kind of analogously to how it got improved for Yang-Mills. But to my big surprise, we couldn't improve it arbitrarily. And in fact, we proved, and Matt Schwartz wrote a second paper where he actually calculated a ton of scattering amplitudes to really prove it. But he calculated it very laboriously with actual polarization vectors and the Feynman diagrams and everything. that the best you could do is something that goes like e over e to the 6th m Planck squared m graviton to the 4th. Okay? So you could improve this energy to the 10th down to energy to the 6th, but you could not do better than that. Okay, and there's an infinite class of theories that you could improve down to this point too, and Matt really showed that, like I said, with very difficult calculations involving the scattering amplitudes to really show that you're not being fooled by field redefinitions and all this stuff, that you could not do better than this. This class of theories that we already talked about with Georgia and Schwartz back then were the theories that were rediscovered by Durham and others many years later as a new mass of gravity. Okay? So, but it's exactly the theories that we were talking about with Georgia and Schwartz already. This class of theories we're talking about a number of years before that. What would be really nice to do is to do all of this analysis on shell. It must be doable in a nanosecond in comparison to what was done before, and really understand on shell what is the correct choice of 3 particle couplings now that allows us best possible high energy behavior for the 4 particle scattering amplitude. Okay, so this thing that I just alluded to is why you know that something has got to go wrong, right? Now you said as you say that there's something that already goes wrong with the 3 particle amplitude. It's impossible to arrange so the 3 particle amplitude comes out right. That's why the 4 particle amplitude cannot come out right. Okay, because if the 3 particle amplitude could come out right, the 4 particle amplitude would have to be okay. The 3 particle amplitude can't come out right, so the 4 particle amplitude must grow with a minimum amount. What would be cool is to figure out, rediscover this good massive gravity theory, this good class of massive gravity theories by exactly this criterion. I think that would be a nice, very nice on-shell exercise. Yeah.
Maybe you should agree
Yeah.
that massive gravity doesn't exist.
Well, no, it's not quite as bad as that, because it's there are some things that are, I mean, there's a lot of things that are wrong with these theories in my own view, and especially when you have 2 to 2 scattering amplitudes that begin like s cubed or like energy to the 6th. They're in really great tension with positivity constraints on anyway, there's a lot of things about unitarity that tell you that 2 to 2 scattering amplitudes cannot begin as energy to the 6th. They have to begin as energy to the 4th. But it's something more detailed than that, which is wrong. It's not something like thou shalt not break diffeomorphism invariance. That's a dumb reason. It's like saying thou shalt not break gauge invariance, and neither one of those have any content because neither one of the symmetries really have any content. So the problem is not with breaking or not a redundancy. The problem is with the physical behavior of the theory, and it does seem like we can't Higgs gravity in the same way we can Higgs Yang-Mills. But if you look at Matt Schwartz's paper, you'll see why there's room for I mean, there's many different components, scalar, vector, and the spin 2 itself. And so, you know, there's like 4 or 9 depending on how you, well, anyway, there's a large number of different scattering amplitudes. And you have to work really hard because you could do something to fix the scalar ones, but it would mess up the vector ones or the other way around. And so there was some work to be done to show that there's nothing you could do to beat this e to the 6th. And yeah, I suspect that has a very, very pretty on-shell explanation.
But definitely there are massive series that have massless limits. And as far as I understand, what you have done can be interpreted as perturbation theory with respect to mass.
It's not exactly perturbation theory. Well, I mean, the high energy limit is perturbation theory in powers of 1 over mass, sure. Sorry, in powers of mass over energy. But it's not perturbative. I mean, the basic construction is not perturbative. So.
What is the behavior? You say that it's non-perturbative. How does it behave?
Oh no, the formulas aren't. But I mean, I'm saying it's not a perturbative approach to mass. A perturbative approach to mass would be just giving corrections that are powers of m over e, m over energy. This is not like that. I mean, that the mass is not a perturbation around 0. So there are some non-perturbative things that I mean, 3 particle amplitudes are fixed by symmetries very often. And there, even for massive particles, amplitudes for 1 massive particle and 2 massless particles are also totally fixed by symmetries up to the strength of the coefficient. So those things have, there are non-perturbative statements you can make about them. When you have 2 massive particles and 1 massless particle, now there start to be some number of structures. So, but even then, there's a finite number of structures. And so I should say, in the world of massive amplitudes, there's another very nice question, which is the following. I think it's a very, very nice question. And I've asked it at many of these amplitudes meetings where people have the gravity wave experts and everyone's excited about using amplitudes method to calculate gravity waves. I think a very beautiful question is, why don't we treat a black hole as an elementary particle and calculate the 3 particle amplitude for 2 black holes and a graviton? Okay? From far enough away, there should be such a scattering amplitude. Okay? And so what is it? In principle, this information is sitting there in the Kerr-metric. Okay? So for a Schwarzschild black hole, we know what it is because it spins 0 and the structure is unique. So there's nothing to do. So, but whether it's a sun or a black hole or a neutron star, the 3 particle amplitude is the same, right? If it has spin 0. But where it should get exciting is when it has spin s, because when you have a, because now there are 2s plus 1 different structures in this 3 particle amplitude. And so a Kerr black hole is making a choice for one of them. So why is it making that choice? What is the choice? What are the actual numbers that show up in the 3 particle amplitude? If you could extract, you can in principle extract this information from the Kerr-metric. You could, for example, do it by looking at very low energy scattering of some probe scalar particle and a black hole. So you calculate that scattering amplitude on the one hand just from the geometry, and on the other hand you calculate it by this Feynman diagram, okay, or by that on shell, by just gluing those things on shell. If this is really far away, really slow, then it's just dominated by 1 graviton exchange. We don't have to worry about the multi-graviton exchange. Okay? It's dominated by 1 graviton exchange, and so we should be able to use that to extract what that 3 particle amplitude is. I think it would be great if we knew what the 3 particle amplitude is. I think it would be great if the 3 particle amplitude was actually correspondent to minimal coupling. That would be really beautiful. Because it would mean that a black hole looks like an elementary particle, which I suspect is compatible with the no hair idea, right? So if there's no way you can tell about substructure of a black hole, if it's really a hole in space-time, then somehow it shouldn't have any features in it that you would ascribe to multipole moments. But that would be really cool, to this idea that black holes are elementary particles. I mean, people have had this vague idea for a long time. They're continuously connected to elementary particles. It would be really cool if the 3 particle amplitudes were those of minimally coupled elementary particles. I don't know if that's true or not. I'm just saying that's one possible cool thing that could come out of this calculation. So once you start thinking about massive particles, it's anything. This chair is a massive particle. I mean, you know, that now we're really talking about any old amplitudes. And of course, you could make yourself feel cool if we knew this, because you could also calculate black hole scattering. Of course, at very, very far distances apart from each other, where they basically look like particles anyway. But still, I think it would be really interesting to get the answer to these questions. 3 particle amplitudes are God-given numbers, right? They're not crappy things. They don't have dependence on momenta, kinematics. They're just numbers. So what are these numbers for black holes? I think it's a very, very interesting question. So that's, yeah. Okay, great. Yes, let's see how many people survive. That's right. Okay?